Welcome to part 2 of lecture 2. So in this part, I just want to kind of run through a series of examples. So it's always good to have a collection of examples to help kind of enforce your understanding. And we're going to see some new vector spaces or see some vector spaces you would have seen before, but we're also going to introduce some new vector spaces. Okay, so let me make myself disappear here, and let's start off with our examples. Okay, so what's the simplest example of a vector space? Well, it's what's called the zero vector space. So this is a vector space where it actually only has one element. Okay, so it has the vector space with only zero. So think of the set with only the element 0. And the way that our addition is going to work on our vector space is that you only have 0 to add. So 0 plus 0 should give you 0. And your scalar multiplication, you take any constant in the field that you're working with and you multiply by 0 and you should get 0 again. Okay, so this actually satisfies all the properties of a vector space and you can go check. So this is in some sense the simplest example of a vector space. Okay. In last lecture, we talked about Fn, and these are the set of all n tuples, right? X1 through Xn, where each of these Xi's belong to F. And we can turn this into a vector space once we define our addition and scalar multiplication in the following way. So we take two elements, X1 through Xn and Y1 through In, and we add them by adding component-wise. X2 plus X2 plus Y2, and we go all the way down to Xn plus Yn. And then scalar multiplication is done by taking a element, X1 through Xn, an n tuple, and we're multiplying it by a scalar, and that means that we're multiplying each entry by that scalar. Okay, and this is something that you're probably familiar with, right? Because this was studied in 1B03. All right, in some ways, this is really just Rn. Okay, so that's the vector space that we're familiar with. Okay, now n in this example was finite, but there's nothing stopping you from just taking a finite list. You could actually take an infinite list, so x1, x2, x3, and just keep on going forever. So that's why we have f infinity here. And we can make this into a vector space by defining addition and scalar multiplication in the following way. So you're taking these infinite sequences, this would be a sequence, and you're adding them entry-wise. So x1 plus y1, comma, x2 plus y2, and you do this for each particular entry. And then the same thing with the scalar multiplication. We're multiplying each entry in this infinite tuple by the constant. And then you can go and check that with these two rules of addition and scalar multiplication, that this makes f infinity into a vector space. Okay. Here's a little bit more interesting example about how you can take any set and you can build a vector space from that. Okay, so here we're going to let S be any set, and we're going to let F upper S be the set of all G, where G is a function from S to F. All right, so I'll write this out. So G is any function from S to F, okay? And F, remember, is either the real numbers or the complex numbers. So to make this kind of concrete, so as an example, let's say we take S to be the closed interval from 0 to 1, right? So these are all the real numbers from 0 to 1, and we'll take F as my real numbers. So R raised to the power of this set S, which is all real numbers between 0 and 1, is all the functions from G that goes from 0 to 1 to R. Okay, so now this set is huge, right? Because anything that you studied in calculus, if it's defined on the interval from 0 to 1 and gives you an output from R, it's inside of this set. So this set here contains many different functions, and it contains many of the functions you would have seen from calculus. Now, it's a collection of functions, okay, but it actually has some additional structure, okay? So it has the structure of a vector space once we define the proper addition and scalar multiplication. And how does this work? Well, let's say I have two functions inside of this set, and you might want to think of your calculus example. You have two functions that are defined on the closed interval from 0 to 1, and you want to add these two functions together. Well, how do you add them together? Well, you take the first function and then you add it to the value of the second function, right? You just add the two functions together that you're used to from calculus. So add two functions together. Okay, so this is our definition of addition of functions. And then the scalar multiplication kind of works the same way. I have my original function, I have a scalar. What should my new function be? In g times c, well, that's the function that I get by first evaluating at g, and then I'm multiplying it by my scalar. Okay, so we scale the function by c. So the interesting thing is that with these two operations, this makes this set into a vector space. Okay, so the interesting thing I want to highlight here is that this works for any set. So there's an infinite number of sets. We can think of all the functions from those sets, and so we can build a vector space from all of these guys. Okay, so suddenly we have a large number of vector spaces. Here's another example that goes from Math 1B03, but I'm using the notation of our textbook, okay? So Fmn is going to be the set of all m by n matrices with entries inside of F. So they could be real or complex numbers, okay? And so in Math 1B03, we use the notation MNF. Okay, so maybe I'll put this remark here, 1B03 notation. And this is something that we actually probably proved in the lecture. And the addition of matrices is the way to add two things, you use the addition of matrices properties, and the scalar multiplication is just multiplying each entry of your matrix by the scalar. And then that satisfies all the properties of a vector space. And the other thing that you would have seen from Math 1B03 or 2LA3 is, the PDF, which is going to be the set of all polynomials of degree D or less. Right, so here's my set of all polynomials. Each of my coefficients are inside of F. And so this is all polynomials of degree let me rewrite that. All polynomials with degree less than or equal to D with coefficient in F. Okay. So the addition of polynomials is just the way that we would normally add polynomials, and then scalar multiplication is the normal way of multiplying a polynomial by a scalar. So this gives you like 6 families of vector spaces, and we'll see them kind of reappear over and over in this course, and we'll see some other examples of vector spaces popping up in the course. But the key thing though to think about though is when we go in this course, we're not really looking at specific vector spaces. We're looking at where V is just any vector space, and then we can apply it to all these specific examples. Okay, so we'll pause here, and then we'll kind of look at what properties we can deduce from the axiom.